facts. So please, bitte.
Yeah. Thank you very much, Patrick. It's always a pleasure to be in this kind of conferences because everybody is talking about contact. We don't have parallel sessions, so you can actually watch every talk. That's great. And of course, as usual, we have a very nice location here. And thank you very much for the organizing team to set up such a nice conference. And also the setting is great, absolutely. So what I will talk today about is a little bit more like simple things. Because some years ago, I had this idea to introduce something which is called third medium. We will see in a minute what it is. And if you do that, then and you try to run contact problems with that, you don't have to do anything. You just have to code another element, and that's it, right? No search, no nothing. That's very easy. And of course, it's something which works, but not for all problems, as usual. I mean, all the normal things do not work for all problems. So if you classically go for contact, especially for large and finite deformation, you have search algorithms, you have non-matching meshes, you have the mortar, the complex mortar method, and Mike Puzo here and Todd Lawson, they are Mr. and Mr. Mortar. So they developed all the algorithms which are now used, I think, in many, many programs, and they work. So I'm not saying that this is not working. You have, of course, the problem that the problem is non-smooth. We had heard quite a bit about that, and we need special algorithms. Now, if you do a certain medium, then what happens is you don't need a special contact discretization. You do not need any special algorithms. You have additional work because you have to sort of somehow discretize this intermediate special medium. It's easy to implement. So, I mean, it took me about half an hour or 1 hour to code this stuff because I just could use a standard element. And you can also tell the third medium to have really the sort of, let's say, physical properties of like air, like gas, whatever, and then you can even use it for thermal contact. So what you want to solve are these type of problems. This is a very simple problem. It's a box loaded on the top, sort of constrained on the sides, and this is the contact problem which you want to solve. And of course, what you can see is this stuff here gets very small, so the elements are squeezed like hell, and somehow you have to account for that in your formulation. So the idea is that this third medium acts a little bit like a barrier method. Once the bodies come closer and closer to each other, you want to have more sort of strength there. You want the energy should raise. On the other hand, the third medium should not influence the deformations, right? Otherwise, I mean, you have different solid problems with the thing. And we have to control the mass disorder. This is a little bit about the history. We started off with that years ago. And then later on, the group of Ole Sigmund, you might know him. He is a very well-known person in optimization. They use that because in this optimization problem, you anyway have to sort of model the whole space. And then doing this, you can also do some contact problems with optimization. So this is quite nice. So that was some work by Bloom, Fredrickson, Dahlklint, and others this way. And then I picked it up again with some ideas. So that was how we started. Simple mesh. The third medium is meshed. And at that time, we said, okay, we compute the right Cauchy-Green tensor, the eigenvalues. And if the eigenvalue is getting very small, then these bodies come close to each other. And then we do an anisotropic material law in the direction of the normal of the bodies. And this will basically formulate this like a standard barrier method. Of course, it's a little bit complicated because you have to compute the eigenvalues. Then you have to insert this into the anisotropic matrix. So but it works. This is some results. This is a third medium mesh, you already see that it's quite deformed. This is a comparison with abacus, so from the eyeball norm, that was fine. But if you look in detail here, the contact at the gap is still quite open, not as close as I showed before. So there is some drawbacks, eigenvalue computations, severe mesh deformation of this third medium. Implementation is a bit complex because in a three-dimensional case, you don't want to compute the eigenvalues of a matrix from that point of view. Now, then we started to do something else with Laura De Laurentiis and one of her postdocs, and we used the isogeometric formulation, which also was working. And then the people in Denmark came and said, okay, we can do it in a different way. And this is what I want to show you now. So we have the requirement. We just use a standard isotropic strain energy function. So we don't do anything. I mean, we are looking at frictionless contact in the moment. And we have an energy function which should not influence the deformation. And the stiffness should be very high once the body is getting close. This is the type of problem you want to solve. You can see even it works even for pointwise contact, which is a little bit funny, right? But it does it. This is our strain energy function. Probably most of you have seen that. It's a split in the isochoric part and the volumetric part. And this is a simple choice. Now note that instead of bulk modulus on shear, and you have a term gamma, which is smaller than 1, which basically acts as the intermediate. So it has very small stiffness, this medium, because if it's 0, I mean, it doesn't work, obviously. And we have to take care of that for J going to 0, the strain energy should go to infinity, and also the pressure should go to infinity, which is done by this log term. You can see it here. If you squeeze this stuff together, you get this kind of behavior. Now, you can implement that, and then you can run it, and then you will see that if you have a problem like this, I mean, it's a little bit hard to see, but you see that here we have overlapping from this point of view. And so that was sort of the big contribution by the Danish group. What you do is you basically add a regularization term to the strain energy function, and then you get something like this. So the mesh deforms nicer and can be squeezed. So how do you do that? I mean, this is actually a paper, something I took out of a paper from them. The idea is you want to constrain the higher order modes of your finite element problem. And to do that, you can use the gradient of f. This one will help you to sort of suppress some of these modes. Of course, gradient of f means you need at least quadratic elements to solve that, at least from the first point of view. And then there were some refinements, and then there were people using instead of f the rotation tensor. So they actually approximated that. Since I'm using this automatic differentiation tool, I actually have done an element with the R, which works, but it's very slow. So I forgot. So when I looked at that at this time, I had this idea that if you have the R in 2D, you can actually compute the angle as a function of the components of f, which is pretty easy. If you have that, you can, of course, then this gradient R, you can put it as a scalar, and so which is actually the same. So you have a regularization function, which is very simple. And if you do it 3D, of course, then the R is not so simple. And my idea was there to do it, simplify it in a way that I used for all the directions this one. Because I don't have to do the correct one. I only have to have something which regularizes. And so this one works fine. So this is sort of a simple way of doing the 3D. All this stuff needs quadratic ansatz functions. And if you take triangular elements, you have also a problem that because the stuff will be constant. So it's not really regularizing. So it only works good for quadrilaterals. Does it work? This is sort of what we call the box problem. it seems to work quite nicely. You see the gap goes to 0, but it doesn't go to 0 like in finite elements, I mean in standard contact problems, but it goes approximately to 0. But this this is sort of 2 and 0.5, so 10 to the minus 4 or 10 to the minus 5 is quite nice. You also have to ask yourself, I mean, how does it depend on the parameter? That's why I did this study. How does it depend on the gamma? And you see, the smaller the gamma is, the more fine you resolve the gap, which somehow is obvious. But on the other hand, the total number of iterations blow up. I mean, they go up, right? Nevertheless, I mean, if you run something like this, I will show some times for that. It's not really a big problem, but anyway, in 2D. The other thing what you can do is you can say my third medium is sort of air. Now you suck the air out. When I did it first time, actually, I sucked a little bit too much, and then I got the result here. I was surprised that the thing was still converging. So it's almost nothing left from the third medium here. And this is for sort of a lower type of pressure in this case. So you can also, I mean, you can also blow it up, right? I mean, that's the other way around, but you can do this kind of thing. Now, here comes the, what the people call the C box. This is a pointwise contact, which you have here. And you can even push it more, and then you get out of a pointwise contact, a line contact again, from this point of view. Now, the idea which we had then, that was our other paper, I mean, what do you do for linear elements? And for linear elements, you can follow different paths. You can approximate somehow the gradient by sort of looking around the element and picking up the stuff. I didn't like to implement that, so I did the easy path, which the easy path is that you basically use sort of a penalty approach here, that this one is sort of constrained by the penalty, and then you have a new function, and then you do the gradient of this function, which means implicitly that you also have the gradient of this guy. But this one is, of course, also manageable with linear elements. So, but we have an additional unknown. And in 3D, of course, you have 3 unknowns. So that's the backdraw, but for me, it was sort of the easiest thing to code, so that's why I did it anyway. And the coding then works. You have the ansatz functions, you have the ansatz for the P, which is the same ansatz, linear ansatz. You plug it into your strain energy, you compute this energy for the regularization, and then you use automatic differentiation, you are done. So that's how I do it, like 15 seconds later, you have the element. And this is how it works. So this is the linear part here now, a linear element. Again, we get the same behavior. And again, we have this kind of thing that if you have a very small number of gamma, you get a very good approximation of the gap. And of course, the iterations on the other side go up. How does it compare now with finite element, node to segment or whatever? And I use here augmented Lagrangian to compare. So if you look at this point here, if the gamma is a little bit too large, then you see you do not pick up really the contact point here. It goes like this. If you use a smaller gamma, then you get basically the same result like the node to segment. But in total, the node to segment fulfills the gap condition up to a machine precision, whereas this one gets stuck at 10 to the minus 4. So as an engineer, you can think about it, can I live with that or can I not live with that? But these are, of course, the limitations here of the method. But from the eyeball norm, it looks fine, right? Because 10 to the minus 4 is quite nice. So we can solve this problem. And if we compare here the load deflection curve with the node to segment approach, this one is sort of the node to segment is line, and the other one is a dashed line. You see that they are quite close to each other. So it works, gives also the correct result. This is how long the time is on my notebook. I mean, the 30,000 elements, something like this, takes one iteration for the whole thing. So the small ones here, 2,000 or 4,000 elements, you see it like a movie going down. So it's quite nice. Of course, if you have more unknowns, then you are in the, but still you are 100,000 unknowns, you're still under it with 100 load steps, right? So that's quite cool. This was one which I tried there. This one is a little bit tricky. I want to know whether this method also could do something like the body movement. This one is like this ellipse. This guy, of course, is pressed in the corner. You have a wall, and no wall. So the idea would be that this one is in the corner, is squeezed there. This one to move out, right? Because like motion. And does it do it? Yes. But you don't want to look at the mesh deformation, right? It looks very crazy, but it really does it. And if you look at the pressure, you get almost no pressure here. There's a little bit of pressure, but classically all the pressure is here. So you can really run this type of problem. This one I picked out of one of the papers of Mike. I think he has done this with Jeremy Solberg. So the idea was you have this load. Actually, I did it on the train when I came here because I said I need something new for my talk. So anyway, so you have something here. You press that down. You move that down, and then here's a beam. This is the red one is the third medium. Then what happens? It starts to buckle, and then you squeeze it together, right? So buckling. There it hits the wall. Then it's squeezed more. And then it squeezed finally like that. So it depends on the, I think yours was even doing more stuff, but it was thinner. So from this point of view. So that's my next stage. I try to run that, that same thing. So anyway, so we can get quite nice results. The interesting part is here I compared some finite elements for the beam. If you take one which I did some time ago with Joshua Courage, which is sort of the best enhanced elements which you can have. It has no hourglassing under compression. And this one gives a different result. Here, this is the blue one, and here the gray one. This is sort of the converged solution, so it's very good. This is a Q1, which is sort of locking a little bit in this kind of application. Of course, you can refine the mesh. Everything is better. But even if I refine the mesh, so this is sort of 2 elements over the width. This is 4 and this is 8. Still, the Q1 doesn't pick up the converged solution. By this one, the TSG6 is already with 4 over the thing, quite good. And this is sort of the load deflection curve here. It's run in this way. This is sort of the lambda, and this is the vertical deflection, and you can see that you need arc length method to solve this problem because it has a lot of instabilities in this case. Can we do it 3D? Yes, in 3D we have a point here, we load that, we push this down and to the side, and then you have a point contact here on this flat lower side of the beam. So this is a little bit a complex problem. So it moves down and to the side, and it looks, so we have a point contact here, which is, if you want to do it with node to segment elements, you need to do the search algorithm. So here you don't need to do anything. You just run it, right? There's another one, which one of my postdocs did, which is quite nice. So you have also this kind of box, but you now do a torsion. And then you get self-contact, hopefully, right? So then what we did, put the third medium on the sides and inside, and you can run these type of problems. So this is with self-contact. Also not so easy with classical finite elements. And the funny thing is with these things, How do I go back? Maybe I can.
You can use this.
Yeah. Shit.
Yeah, I can.
Can you start it? I mean, you. Yes. Okay. Great. So this is how it looks like. And classically, these things run on the first step. So I mean, you don't have. I mean, you have to look a little bit on about the gamma, how to tweak it. But if you know and you have some experience, and there are some design criteria how to do it. This is what we do. You have pneumatic robots. So this one is something a member which has a chamber, and in this chamber you can put some pressure. So you press these guys together. And then you get sort of bending with this type of device here. You see here the pressure, and there's a third medium sitting in between, and then you have contact, and due to that, you get this movement here in this case. Okay. We also like to work on virtual elements. Can you do virtual elements for the same thing? Of course you can. So this is sort of a mesh with virtual elements also works nicely, and you get this type of result. And actually, this mesh here this is a good thing with the virtual element. It's non-matching. You basically put extra nodes. Here you can see it also non-matching mesh, but this is matching in the way if you have virtual elements. This is a fine mesh, passes the patch test, and again you can run this kind of thing. It works quite well. Oops. Here's the last one, which my student, Dr. Xu, did, or the postdoc. It's sort of some guys which are pressed inside, and then here's a long beam, which you either can clamp on this side and on this side, or you can actually also not clamp it on this side, and then you get this kind of behavior for the contact, or this one where it moves back on. So this is what we can do. Now, the last time of the talk, I still am okay, right? Yeah. I sort of like to move a little bit into heat transfer, where now this third medium has some properties of a gas, and of course, we need some equations. We are here, right? I mean, so this is a classical thing, a weak form for the mechanical part, a weak form for the thermal part. We use the classical split of the deformation gradient, which is multiplicative, and then we can sort of put in here a thermoelastic strain energy for the solid. This is a little bit simplified. Classically, if you have a rubber material or like rubber or whatever, you have to take care of the change of the bulk modulus and the shear modulus related to the temperature, which I have not done yet. But this is easy from the point of view. It had nothing to do with the contact, it's just something else. We have a coupling, thermoelastic coupling. We have the Fourier law, which is written down here for the reference configuration. And then you can set up your potentials. I always like to use it. I mean, for thermomechanical problems, you don't have a real potential. But I always like to do it with a pseudo potential. It has one reason. Using the pseudo potential gives you the fastest code. So if I use automatic differentiation, I don't know why, but it really produces the fastest code. The old way, what we did for large strain, going to the sort of current configuration, actually produces an automatic differentiation slowest code. But it was easier to code for us in the old days. Anyway, so this is what we use, and you take the strain energy, and then you have to fix some variables when you do the differentiation, which I have shown here. In this case here, the thermal parts. The thermal parts here have to be fixed during the iteration, the first derivative, and then everything is fine. I use a monolithic scheme. I mean, often people use sort of staggered schemes for this thermal analysis, just a monolithic scheme. And of course, you have to do something with the heat conductance at the interface in the contact zone. And this, of course, depends on the pressure, which means it depends on the LNJE, and can switch between the coefficient of thermal if you have complete contact, and the gas conductance in this case with the pressure dependent. And again, we want to solve these things. We do the regularization, but this one you only have to do on the mechanical part as classic. Here are some results. This is basically a simple thing. It's basically like a one-dimensional example. You have some displacements, you have some thermal parts. This one is sort of the boundary condition down here, and then you have a third medium. And if you don't do anything, you have a temperature distribution like this. It's sort of a stationary heat conduction problem. And if you press it down, then out of a sudden you get that, which is also clear. This is sort of the standard heat conduction which you have in such a situation. I only did it because I wanted to compare to the analytical solution, which seems to be quite nicely in that way. We have some more results now, but I didn't put it here because time is limited anyway. Now, the next thing is, of course, to do a little more complicated. So we have here now a temperature which only acts on one half, and also the displacement is acting on one half. And then here we have one body, the other body, and here's the third medium. And this is before we start the deformation. On the upper part, we have the full temperature. And here we have zero temperature because there is no conductance in this thing. And here's a little bit conductance through the gas. Now, if the contact comes into the play, then it's like that. And notice that the contact law is such that it's pressure dependent. It's like, I mean, if you cook something on a plate with an electric oven and you put the pot on top of it, it will boil after a certain while. If you press the pot down, it boils faster because you get sort of the spot conductance, the spots are larger, and then the conductance is higher. This is sort of this thing. And then if we basically have the final deformation, you see very nice distribution of the temperature here. A nice distribution of the temperature over this part. And of course, we can also show like a little bit of a movie. So you press it down, and then you see the contact here, and then you see the development of the sort of temperature over this type of body. And of course, we can also run our classical problem, which I said, where the one ball moves out. And then the question is, does this also work for this thermomechanical part? See, we have here 18,000 elements, so you can run it easily on whatever. Again, the result is here for the final configuration. You have that thing. This is sort of the pressure. But it's run on the thermomechanical part, so we have here as well temperature as displacement. So this is the pressure distribution, and this is the distribution of the what is this? The QT, sort of the how do you call it? Not the temperature, the heat transfer. Anyway, but you can see that you have here a little bit of temperature, so because it's very close by. And this one shows a little bit this part. So this is how it moves. In the beginning, we have, I mean, this is very small numbers. We have some heat transfer going through the gas everywhere. Once this thing gets into contact, which you can see here on the side, it's getting closer. This one basically disappears. So all the heat flux goes in this direction. And then when it moves out, it comes back again in contact. So you still have a little bit of heat flux here. And then it moves out completely, and then the heat flux is also gone. So it's a quite complex process, but you can actually run this quite nicely with this type of contact formulation. So that's well, it takes a little bit of time, but I think that's still okay. And then, of course, you can use this also for homogenization purposes. So if you want to homogenize at the contact interface, classically, I think it's out of my book. I stole it from my own book. The spot conductance, you have the gas conductance and so on. And so your conductivity depends on the pressure, on the temperatures. And I wanted to run the same kind of thing with this. So you have a waviness here and a waviness there, which is different. See, we have 6,000, 8,000 elements, 30,000 number of unknowns, analytic schemes. We use 45 steps. And if you look a little bit more in detail, you can see here the behavior. And I mean, I grew up with consistent tangents, so this is really Newton convergence. So I always need to see that, otherwise I'm not happy. So this one also works quite nicely. And if you do it again, then in the beginning, all the temperatures here, there's a little bit in the gas. In the next step, you see the contact starts to evolve. There you have something in the gas, and then you have the contact going over this is the temperature distribution. And then if you squeeze it together, finally you get this kind of result. So you can do this kind of thing quite easily without any big coding. And of course, this can also be extended to 3D. And in 3D, what we do is we have this type of elements. I have used here linear elements, but you could also use, of course, quadratic element. It doesn't matter. Here is one block. Here is the third medium. Here's another block. And the upper block is loaded like this and has some temperature on top of it and also some displacement. And this is sort of the deformation which you get. This is for relatively coarse mesh. This is for refined mesh. And you can see here, of course, the deformation. What you also can see here is that the contact in this case, due to the deformation, actually is not anymore node to node, but it's sort of shifting on the side. And the little elements which are sitting in between, they are squeezed and sheared, but they still somehow transfer the temperature and the loading in a correct way. And of course, if you compare the coarse mesh and the finer mesh, then of course you get better results for the temperature distribution. And here we have the same for the stress distribution. You can also see that, of course, the finer mesh here will give you a better distribution. You can, of course, refine that even more. Now, of course, the question is, how long does all these kind of things work? I always like to monitor the times. So if we have an 8x8x4 on my laptop, which is from Apple, I have 148 iterations. The solver time is 3.6 seconds for the whole thing, not for one, for the whole thing. And the computation of the tangent and the residual is 0.5. So this is manageable. And if you get a larger mesh, 12 by 12 by 12, you have 2,000 unknowns, 2,000 elements, 18,000 unknowns. So we are talking here about 30 seconds for the solution. If you have a 16 by 16, it's still working fine. So it's about 2 minutes, 3 minutes to run. If you are 24 by 24, of course, you get caught by the solver. So, I mean, if you then have a good solver, you can, of course, I mean, I use Paradiso, which is not bad, but for these type of problems, I think it's better to have some nice solver, which has a AMG or whatever inside, which I don't have. And of course, if we reduce the gamma, then we also reduce the number of iterations, and of course, then you also reduce the time to solve them. But I just wanted to say that. Now, this is actually the end of my talk. Maybe I'm a little bit early, but anyway, we have time for discussion. So what are the achievements? The achievements is we have no contact search. It's very easy to implement. Every grad student can do it. I mean, if he has sort of a hyperelastic element, to change that hyperelastic element into this element is pretty easy. You have to do two things. You have to change your strain energy function. You have to put the regularization term, which of course is a little bit of a thing. We can add physical properties to the third medium, which is nice. So we have some additional knowledge which we can put. At the moment, I haven't done the friction. It's a little bit tricky. I was thinking about it. I mean, there is a paper actually by the group of Sigmund. They did something on the friction. You do something like crystal plasticity approach. I'm quite sure. I mean, yeah, you have to change, and then you have to do the directional plasticity in one slip line. Yeah, and that's the idea. But the thing is, I mean, to find out the normals and things like that. So I'm thinking about something which is easy to code, right? I mean, you can do it brute force, as classically in contact mechanics, but I was thinking about this. So this is something I'm working on here. Friction plasticity actually is easy. You only have to put it in your solid. I mean, this is sort of for free. There's nothing much to do from this point of view. Now ending, I have to say this is a method, and I showed you it works great, right? But I didn't show you all the examples and also not the examples where it doesn't work. So I mean, there are also examples where you have a problem with this method, and one has to be always aware. I'm old enough to be able to tell you, right? No, I mean, one has to be aware when you want to solve this problem, because what can happen is that if you have a very large sliding, that then you are sort of pulling the element very much. And then if it moves around the contact, then out of a sudden you have a stiffening of your system, which is not correct. So, I mean, you have to be, this has a certain range where it works great, but there are some parts where you still have to do the good old contact and everything to get it. And also if you have, think about it, large rotations, if you have a large rotation of your problem, with a third medium to rotate something in there, you get the same sort of thing, you get stiffening in that way. So one has to be a little bit careful. It works for the application which I have shown you, but it has some limits for all the things. I always like to say that because you have to know as an engineer where to use it and where not to use it. So from this point of view, it's nice. So thank you very much for your attention. Maybe I was a little bit too fast, but I hope you got the message. Thank you.
Thank you, Peter. Beautiful results. So talking about the perspective, the outlook, when you say add physical properties to the third medium, could you also look at fluid entrapment and look at viscous?
Yes, I think you can do that, yeah. Mm-hmm.
And then if you do this, because as you squeeze things, if you have a very soft solid that you drop, you have an impact, and you trap some gas underneath, you trap a bubble. As the solid is approaching, your thickness of your third medium is decreasing to 0, and your mesh is heavily distorted. So in what you present, right, you can squeeze those elements.
Yes.
But if you want to model viscous flow, what do you need to adjust in the method to
Yes, I think you have to adjust it. I mean, you have to look at it, whether it works or not. I mean, one has to try to implement the viscous properties, and then you have to see whether it works or not. Because, I mean, as I said, I mean, if you have very much a lot sliding, I mean, you squeeze, I mean, what happens, I mean, this thing, if you put it down, then you squeeze the stuff out, right? So it moves quite a bit on this side. But think about it, I mean, when you began, you had a mesh. And this mesh actually is sitting, the nodes are still connected. So you have to be able to cope for this sliding, which is done by the regularization, but only, let me say, for smaller portions, not for large sliding. So I think that's also the problem. If you have large friction, then eventually it doesn't work. But for small friction, and if you have small movements, I think it will work.
Thank you for the presentation. I was wondering if it could be extended to include adhesive effects or adhesion.
Adhesion. I think it should be able to do that. You have to, of course, model a little bit about your model, but in the interface, I think you can also put some adhesional forces in there. That would be possible. but I have not tried it. So I mean, I cannot say it really works, but I think it's possible.
You have 2 blocks with a 0 gap, and you start the problem.
Yeah, the question from yesterday, right? Yeah. I haven't done that, right? I mean, I think you need to have this sort of 10 to the minus 5 gap, right? I mean, to start with, then you can do it. Yeah, I think that's the same. I mean, if you run anything with a barrier method, I think you cannot put this stuff on top of each other because then it blows up.
Yeah.
So I mean, that's the same thing here.
I think that you can do it. When it converges to something 0 away.
Yeah. I mean, but you know, I mean, the problem here is if the gamma is getting too small, I think eventually the element want to work, but you have a highly ill-conditioned problem, right? Because you have a very much of a stiffened thing. So, and I haven't looked into the solver kind of thing. So eventually one can do something about it, but I haven't looked at that. I just took all the stuff which you have on the shelf, right? And no tricks. But yes.
Thank you, Professor. So the idea is to never remesh.
Yes, at the moment, yes. Yeah. Well,
If we think a large rotation of a disk, for example, it would be possible to remesh.
Yes, I think that's another thing you can do. You can remesh. I haven't done it. You know, I'm sort of I'm a retired professor. I'm a postdoc. I have to work on my own. So then it's not so easy to ask somebody to do the remeshing thing. But I think we can do that. Yes.
Could you do it with the background grid and then you cut elements in there?
Yeah, that would be another possibility. You mean the Mats Larsen, Peter Hansburg thing, right? Yeah.
Then the mesh with the back.
Yeah. Yeah. Yeah, that's a good thing. Yeah, that could be done.
Any other questions? Maybe I have one, maybe a very naive one. What are the guidelines to choose the constitutive behavior for the medium?
Yeah.
Is it, do you choose the stiffness must be very low? Is it good to take it as low as possible?
Yeah. Well, it's good. I mean, if you want to fulfill the gap condition, maybe I showed it. Now it's several slides ago, but if the smaller the gamma is, which is a constitutive parameter, the smaller the gap will be. If it's too small, then you run into problems because of ill conditioning of your system, so you cannot solve that. From the theoretical point of view, of course, gamma goes to 0, also gap goes to 0, right? Because then the log term only picks up if you're very, very close to the basically contact line or contact surface. So this is fine, but from this point of view, we are limited by the computer precision, and then so this is why we cannot use a very small gamma. You could think about some stuff, but that's it. So basically, we have some experience gamma to be. I mean, you can link it somehow to the bulk modulus of your sort of solid, and take it like 10 to the minus 6 or 7 times smaller than what you have in the solid for the bulk modulus that works. And then we also have in our papers, we have set up some ideas how to choose the regularization parameter. So the thing is actually what you want is to have a method which is a little bit independent on the choice of the thing, right? I mean, otherwise for each problem you have to find another thing, but the idea is to have sort of a set of variables which you don't have to change all the time, so that they work for a larger class of problems. This is what you can actually achieve by linking it to some of the physical properties.
Okay, I see. But there is a part of trial and error in the end of the final adjustment.
Yeah, there's, I mean, it's not I mean, I have no real design rules to do that, right? I mean, There are some rules of thumb which always work, but it's not a real design rule from the mathematical point of view, if you want to say it like that. Okay.
So, if no other questions, we thank Peter again.